Hello, Algebra 2. This is Mr. Szabo again. In part 2 of this lesson for section 2.6, we are going to talk about reflections. When we reflect, we are always reflecting right now over either the x-axis or the y-axis. So if we are reflecting, it'll be the x-axis, here's my x-axis, or the y-axis. So there's a couple of key pieces of information that we have to understand. First, I want you guys to plot any ordered pair. So on the x-axis graph, choose an ordered pair, label it A. On the y-axis graph, choose an ordered pair and label it B. Write down what the ordered pair is. Make sure whenever you're writing an ordered pair, you are writing it in parentheses. So for my example, I'm going to use the ordered pair -6, 3. So I'll plot that ordered pair A, and I'll use the exact same one on the next one, and that's totally fine, and use B. So if I am reflecting over the x-axis, that means my next point, or point A, is going to be reflected over the x-axis. It's going to go from 3 units above it to exactly 3 units below it. I'll plot this point and I'll label it A prime. And then I'll do the same thing with the point B, except now I'm reflecting it over the y-axis, over my vertical axis. So it's going to go from here all the way to the other side of the y-axis, which is going to be at this point, which I will label B prime. So B prime moved to 6, 3. A prime moved to -6, -3. What happened to the coordinates? So specifically, what happened to the x value, or to the x coordinate? And what happened to the y value, or the y coordinate? I want us to see that obviously the x coordinate, -6, stayed the same. It didn't change at all. And the y coordinate went from +3 to -3. We call that being opposite. That's going to be the case for every ordered pair in a graph as we reflect over the x-axis. The x stays the same, the y value becomes the opposite. And then it's kind of the exact opposite with the y-axis. We see that the x value is now the opposite, and the y value stayed the same. So with function notation, if we are going to reflect over the x-axis or y-axis, the functions look a little bit different. So if I'm reflecting f of x over the x-axis, since the x value stays the same and it's the y value that becomes the opposite, my function f of x, the x part of the function stays the same. Since the y value is opposite, it's the opposite of f of x, because f of x represents y in that function. Similar, I have f of x here, but this time the y value stayed the same, so my f of x is going to still be positive. The x value is the opposite, so my negative goes inside here. It's the opposite of x in the function notation. I hope you didn't work ahead on these two, because I'm going to change the functions around a little bit. After I printed this, I decided I don't like using x squared right now. I want to use the function f of x equals 2x plus 1, and we can use that for both options. So we're going to use a linear function. In this example, h of x is the reflection of f of x equals 2x plus 1 over, well, since this is in the x-axis, we're going to stay over the x-axis. Now, h of x is going to then be equal to the opposite of f of x. This is where you have to be careful. This is going to be over 2 steps here. F of x is 2x plus 1. But I need the opposite of that. So I'm actually going to put this in parentheses. I want the opposite of the whole thing. So I'm actually, after distributing this, going to have -2x minus 1. That's the function that represents the reflection of the original function, positive 2x plus 1, is going to be negative 2x minus 1. That's going to ensure the opposite y value, but the same x value. And then if I'm reflecting over the y-axis, I'm now going to be taking the original y value, but change my x value. So that, when I'm plugging into my function, looks different. I'm going to have the opposite of my x value, not the opposite of the whole function. So in this case, 2 times negative x is going to get me negative 2x, but I don't distribute it to this plus 1. This is going to ensure that my x value is the only opposite. The y value will still remain the same. Here is my new function. Alright, so now let's go ahead and flip and let's do a quick summary of all of our transformations that we talked about today and talk about our reflections, or translations and reflections. When we are translating vertically, we are adding or subtracting to the original function. If it is a shift up, I am going to add a value. A shift down, I am going to subtract that value. Then we talked about horizontal translations. That is adding or subtracting to your x value. And again, this was the tricky one. If I shift to the right, you think that it's positive, but it's not. I am subtracting h. And a shift to the left is adding h. Go back and watch the first video if you want to see an example of why. And then the ones that we just did, if I am shifting or if I am reflecting in the x-axis, so my x-axis means my reflection is actually a vertical reflection. A ordered pair is not changing its x, it is only changing its y. That's when I have the opposite of f of x. If I'm shifting or reflecting, I should say, in the y-axis, y is vertical, so the reflection is a horizontal reflection. My x is changing, is becoming the opposite, so if that's my y-axis and that's my x-axis, then the x is changing, so it's f of negative x. Okay, the last thing I want you guys to be able to do is to make some descriptions of what's happening, both to the graph and then to the x values and to the y values. I'll do part A with you guys, and then I'll go ahead and ask you guys to finish off the rest and see how you do with this. So for part A, it says, given this parent function of y equals x, so that's my parent function, what is happening to the graph and what is happening to each of the ordered pairs? So when I look at this, I can see this is happening. You can look at it as happening either to x, or you can look at it as happening to the entire function. I like to look at this in a linear function is always a vertical or a vertical, so up or down change. So since I'm subtracting 1, I am going to shift each point or each ordered pair down 1 unit. That's describing what's happening to the graph. Each x value then, since I'm shifting down, the x value is staying the same. Each y value, now I'm not reflecting at all, so I'm not talking about opposite, but I'm shifting down. So for each y value, it's going to subtract 1. Go ahead, pause, try part B. So for this one, again, I say that this is a shift up 10 units because the way I see it, I've taken something like 0, 0 and moved it to 0, 10. I look at from the input values, and my input stayed the same. And my output, I add 10. But you could have said that you shift this left 10 units because you can see it's still a shift left 10 units, and then your y value would have stayed the same, and your output or your input value is subtract 10. So technically, for linear equations, it could be either 1, but you just have to be careful with how you describe what's happening to each input or output value then. And you can see from the graph, shift up versus shift left, it's not going to be any different. All right, go ahead and take a minute again, pause, and try to fill in our tables. So to start, I'm representing that if I'm shifting this to the right 2 units, my y values, or the function's value, is not changing. If I am shifting it down, now my x changes, or does not change, my y will. And if I reflect over the x, x stays the same. Whatever axis you reflect over, that coordinate stays the same. Shifting right 2 units is going to add 2 to my x-coordinate. Shifting down will subtract 4 from my y-coordinate. So the last thing I want you guys to do is see if you can write new functions based on the given transformations here. So if I give you this parent function and I ask you to translate this up 2 units, is an example, I'm going to call this new function h of x, and up 2 units means that I'm going to take f of x and add 2 to the whole thing. So I get 2x minus 3, that's f of x, plus 2. Now I don't need the parentheses anymore because I was just adding and I have to combine my like terms. H of x is going to be equal to 2x minus 1. That is a translation up 2 units. So the last thing I want you to do is see if you can come up with what B, C, D, E, and F are. Press pause, and when you are done, unpause to check your work. So I'll describe part B real quick here. It's a translation left 5 units, so f of x is going to be x plus 5, which means, and I'll do this off to the side here, I'm taking 2 times x plus 5. I'm basically substituting x plus 5 in for x, minus 3. So I'll have to distribute 2x plus 10 minus 3 and combine like terms. My new function, h of x, is going to be equal to 2x plus 7. That's going to represent the shift to the left 5 units. So for each of the last 4, I showed in red what transformation we were doing, right 6, down 1, how I substitute it into the original function, and then what we get for our new overall function. A reflection over the y means I take the opposite x. A reflection over the x is the opposite y. I have to distribute, and then reflect over the x and shift this up. I reflect, then I shift. Don't forget you can always plug your original function or parent function into Desmos, and then plug your new function in and just see, does that represent exactly what you were looking at or what you were looking for. So tomorrow we are going to go ahead and take this to another level by looking specifically at a certain type of a transformation that we didn't talk about today. Today was about translations and reflections. Tomorrow we'll talk about stretching and compression, and vertically stretching and then compressing. And we had the main focus today here with our functions and equations and graphs and how we were doing the translations and reflections.